everyone, welcome to today's lesson. We are on lesson 1-9. In this lesson, what we're going to learn is how to apply an algebraic method for testing symmetry with respect to the axes and the origin. Our language objective is to explain the steps we use when applying an algebraic test for symmetry. So let's take a look at our do now. For today's do now, what we are going to be doing is we're going to be plotting points on our grid and comparing them. So I want you guys to pause the video, try all 7 questions out, and let's see if we have the same answers. All right, so here is my graph and here are my answers. For number 3, we see that A and B are reflected over the y-axis. For question 5, we can notice that A and C are also a reflection, but this time over the x-axis. And for number 7, A and D are a reflection, specifically over the origin. So what we're going to do today is something that you have seen in your geometry class in the past, and we're just going to apply it to functions. So let's take a look at our thinking. So for today, what we are going to be looking for is how do we check symmetry graphically and also algebraically. So let's look at the graphic test for symmetry. There are 3 things that we're going to be looking for. We're going to be looking for symmetry over the x-axis, symmetry over the y-axis, or symmetry over the origin. A graph is symmetric with respect to the x-axis if whenever we have a point x comma y on the graph, x negative y is also on the graph. So let's say I had a point here, positive x, positive y. I know I have a reflection through the x-axis because my point is going to be somewhere here. So in this case, what changes? The y value. A graph is symmetric with respect to the y-axis if the point x comma y is graphed on the graph, but also negative x, positive y is also on the graph. So in this case, I have my point here, my original point x comma y. If I have a reflection through the y-axis, my reflected point would be somewhere here. And in this case, what would change? The x. And our last case, we have symmetric with respect to the origin. A graph is symmetric with respect to the origin if whenever we have the point x comma y on the graph, negative x, negative y is also on the graph. So let's say I had my point here, my original point x comma y, my reflected point would be somewhere here. And what happens? Both x and y change. So that's a graphic approach, looking at the ordered pair. We will also need to do algebraic test. So there's 3 cases here as well. Number 1, symmetric with respect to the x-axis. Just like we said graphically, a graph is symmetric with respect to the x-axis if when you replace that y with negative y, just like we said in the original right here. This time we're going to be looking at functions, so we're going to look to see if we have the same exact function that we started with. Number 2, if we have symmetry with respect to the y-axis, so a graph is symmetric with respect to the y-axis if when you replace x with negative x, again you get the same function you started with. And lastly, symmetric with respect to the origin. A graph is symmetric with respect to the origin if when you replace both the x's and the y's to negative x and negative y, you're going to end up with the same exact function you started with. The algebraic approach or the algebraic test actually takes into account that graphical test that we have seen already. So let's look at some examples. Let's start with the graphic test. So for number 1, we are going to be given a function f of x specifically. Looks like an absolute value function. It says determine the function's symmetry graphically. So what we're going to do is we're going to graph this function. You could use your calculators or you could use your knowledge of how functions are shifted to graph this. All right, so here's my f of x function. When I am doing a graphical test, what I'm going to do is I'm going to pick a point, any point I want whatsoever. I'm just going to pick this point right here. So that point is located at 1, 4. And what I'm going to be looking for is this point somehow reflected through the x-axis, through the y-axis, or through the origin? And I see its reflection point right here. So this point goes to -1, 4. And in this case, what happened? What changed? The x value changed. If the x value changed, that means that we have symmetry with respect to the y-axis. Number 2, we have been given f of x is a cubic function this time. We're also determining the function's symmetry graphically. So I am going to put this on my calculator. If I know how this function looks, because it is a parent function, I could use that knowledge as well. All right, so here's my function f of x. I'm going to do the same thing I did before. I'm going to pick a point. I'm going to just pick that point 1, 1. And I'm going to see if I could find the point that's reflected with that point. And I do see 1, -1, -1. Both the x's and the y's change, which means we have symmetry with respect to the origin. So that is if I have been given a graph. If I'm given a graph, what I want to do is look at the ordered pairs and see if I have some sort of reflection going on. Let's look at an algebraic test. So here in example 2, we are applying an algebraic test for symmetry. So for number 1, we have been given our function f of x. Rewrite this just a little bit because it cut off. So we have been given our function f of x, and we want to check for symmetry about both the axes and the origin. So here's the setup I have. I have symmetric with respect to the x-axis, the y-axis, and the origin. So we have x-axis, y-axis, and origin. That's what we want to test. So when I am given these types of questions, the first thing I tend to do is I do a quick graph on the side, on the bottom, somewhere, so I could kind of remember what this means. So if I have symmetry to the x-axis, that means that I have reflected through the x-axis. So if this was my original point, where would my new point lie? Somewhere down here, which means what would have changed the y? So I'm just gonna put -y there. So I remember that. I'm gonna do that again for the y-axis. So here's my quick grid. If I have a point here and I'm reflecting it through the y-axis, where would it go? It would go somewhere here. So again, what would have changed? The x. And origin, I tend to remember mostly. So I know that both the x and the y change. The order doesn't change. Everything is exactly the same. But if you want to see it graphically, again, your quick graph here. Your point was somewhere there. Where would it go? It would go down here. What would have changed? Both the x's and the y's. So that's just a quick way for me to remember how things are reflected. Now what we are going to want to start off doing is rewriting our f of x function in terms of y equals. So there's my original function. According to the algebraic test, if I have symmetry to the x-axis, what I'm going to change is the y to a -y. So I'm going to change that y to a -y. Everything else stays the same. And what I'm going to do is simplify and solve for y. So I'm going to divide by -1. And when I divide by -1, I'm doing keep, change, flip, but a trick is all my signs for the numerator are going to change. This is what I get. Now I'm going to compare what I got to the original function. Are they the same? Do they look exactly the same? Clearly not, which means that I don't have symmetry with respect to the x-axis. So not symmetric with x-axis. Let's see if we have symmetry with respect to the y-axis. So I'm going to start off the same way. I'm going to rewrite that function. This time, what am I changing? I'm changing that x or x's. Anytime you change, you need parentheses. So all I did is change that x to a -x. I'm going to simplify here and see what I get. All right, so this is what I got. Now I'm going to compare what I got with the original function. They are exactly the same. Since they are the same, that's good for us. That tells us that yes, this function is symmetric to the y-axis. Let's do our last test because that's what the problem was asking us to do, all three. So I'm going to start out with the original. In this case, I'm replacing both the x's and the y's. I'm going to simplify. I'm going to compare what I got with the original, and we have not symmetric. So for this specific function, I have a function that is symmetric to the y-axis. Let's look at the next one. So for number 2, we have been given our function f of x. We want to test this function to see if it's symmetric with both of the coordinate axes and the origin. So in this case, I'm going to set myself up. First thing I'm going to test is the x-axis. If I'm testing the x-axis, what's going to change? I'm reflecting it through the x-axis, the y changes. So I'm going to start off by rewriting the function in terms of y equals. In this case, I'm going to change that y to negative y. I'm going to clean it up, simplify, and now I'm going to compare to the original. Clearly not the same, which means not symmetric. For this one, I'm just going to write not symmetric. I'm going to line it up. I'm going to go to my next one, the y-axis. I always do it in this specific order just because I like ABC order. So I start with the x-axis, the y-axis, and lastly, always the origin. So if I'm reflecting through the y-axis, I am going to change my x. Again, I'm starting with the original function. I'm going to replace all of my x's. In this case, I have multiple. I'm going to simplify and try to clean this up if possible. And this is what I get. Again, I'm comparing to the original, not exactly the same, which means not symmetric to this axis as well. And lastly, let's see what happens with the origin. So in this case, I'm changing both the x's and the y's. Starting with my original function. So I want you guys to try this and let's see if we have some sort of symmetry. So I see that I have symmetry with respect to the origin for this function. So keep learning, keep growing, and I will see you in our next video.